Hi again, welcome to the next video in the calculus series. In this video we introduce the technique of integration, which is sometimes called anti-differentiation. It's a powerful technique and completes the two-way exchange between Leibniz and Newton. In a previous video we saw that differentiation is synonymous with finding the gradient of a function at any given point. In a subsequent video, we will see that integration is synonymous with finding areas. The process of finding a gradient function, sometimes called a derivative function, given a basic function, has already been dealt with at length. For example, if we are given y equals 3x squared minus 10x plus 5, we can differentiate to obtain dy dx equals 6x minus 10. Remember, the 5 disappears because it's a location constant. It does not affect the gradient. To follow the ideas of Leibniz and Newton, the question immediately arises, if we are given a derivative function, can we find its original function? Well, yes, we can. We can just work backwards and retrace our steps. So the reverse of differentiation is sometimes called anti-differentiation. If we start with the function dy dx equals 6x minus 10, we want to do the reverse of our differentiation steps to obtain y equals 3x squared minus 10x. Don't worry about the 5 just yet. The antiderivative of 6x minus 10 is therefore determined by, let's take the first term. First step, copy the constant in front of the x, which is 6. Rewrite the x, so 6x, add 1 to the index, 6x to the 1 plus 1, which is 2, or 6x squared, and then divide by the new index, 6x squared over 2, which gives us the 3x squared. For the second term, which was minus 10, we write that down, and that's really minus 10x to the 0, because x to the 0 is 1. So we now add 1 to the new index, so it's minus 10x to the 0 plus 1 equals 1, and we divide by the new index, which is simply 1, leaving us with minus 10x. So the antiderivative of 6x minus 10 is 3x squared minus 10x, but we can't stop there, we need that constant term that we had in the first case. The antiderivative is more commonly referred to as being the integral. To show we are taking the antiderivative of a function, say of fx, we start by using the symbol in red and follow it with the function itself. But then we must always add an indication of what the variable is subject to this integration. Here the variable we are integrating with respect to is x. So we add dx at the end of our statement. So the integral sign of 4x plus 7 dx. And that 4x plus 7 sometimes can be in brackets and sometimes it doesn't have to be in brackets. When it's not in brackets, then we know that everything between the integral sign and dx is going to be integrated. And then we can say the integral of 4x plus 7 with respect to x gives us the answer of 2x squared plus 7x. Finally, there is an extra bit we should almost always include. When we differentiate, the constant in our function is left off because the constant only tells us about the location of the function on the axis. So it does not contribute to our understanding of the gradient. When we integrate, however, we need to add the constant back in. The result of our integration produces the correct shape of the curve, but the curve could be located anywhere, up or down. To overcome this omission of location after our integration steps, we simply write plus c at the end to indicate the curve could be located up or down by c units. It expands our understanding by locating the curve on our axis. The integrated bit with the x terms therefore gives the basic original details of the function. Hence the function resulting from integration is referred to as a primitive function because it is the form or expression from which another can be derived. So to summarise, we have a question: find the primitive of 14x cubed plus 6x squared minus 12x plus 42. We have 4 terms and we just repeat the same basic steps 4 times. So 14 we write down, x, add 1 to the index, 4, divided by the new index, 4, plus 6x, add 1 to the index, makes it a 3, divide by 3, minus 12, x to the 1 plus 1 is 2, so divide by 2, plus 42x plus the constant term. Tidy up by simplifying the fractions. We get 14 over 4, which goes to 7 over 2x to the 4th, plus 2x cubed minus 6x squared plus 42x plus the constant term c. The question might also have been expressed as find the integral of the function with the x at the end. It's exactly the same question, so it can be asked in 2 different ways at least. Corresponding rules are applied when integrating terms with negative indices or with fractional indices. So for negative indices, we might have integral of 5 over 7x cubed dx. So rewrite that as 5 over 7 integral x to the minus 3. Leave the constants out the front. Bring the index up into the numerator. So we now integrate that in the normal way. Write down the constant, 5 over 7. Then x to the minus 3 becomes x to the minus 2 over minus 2. So we have a minus in the denominator, so put that out the front. 5 is in the numerator, 7 times 2 equals 14 is in the denominator. Bring the x to the minus 2 underneath to make it x squared, and don't forget to add the plus c at the end. An example of a fractional index, which is very common, is the integral of the square root of x dx, which of course, like with differentiation, we can rewrite as an index. So integral of x to the half dx. Then we add 1 to the index, so it becomes x to the 3 over 2, and then divided by 3 over 2, which is the same as multiplying by 2 over 3, plus c, and then rewrite it so that it looks nice. X to the 3 over 2 can be written as 2x root x over 3 plus c. In passing, at this stage, don't try to integrate 1 over x dx. We'll worry about that later on. It's got to do with logarithms. There is also an equivalent process for the differentiation strategies we call the chain rule. For differentiation, we had a structure, which we must recognise, of y equals 2x plus 3 to the 4th. We had one term in brackets raised to a power. So when we differentiated that, we brought the 4 down the front, we rewrote the brackets, 2x plus 3, took 1 off the index, 3, and then multiplied by the derivative of what is inside the brackets. In this case, the derivative of 2x plus 3 is 2, so therefore multiplied by 2. Tidy up, we got 8, 2x plus 3 in brackets, all cubed. If we have the same kind of structure for an integration or anti-differentiation, it could be that we have the integral of 2x plus 3 in brackets, all cubed, dx. Well, pretty much everything in reverse. Here we start by rewriting the brackets with the 2x plus 3, adding the 1 to the index, 3 plus 1 is 4. Then we divide by the new index, which is 4, and we also divide by the derivative of what's inside the brackets, which is a 2. And then we tidy that up to give us 2x plus 3 to the 4th over 8 plus the location constant c. We do not, please not, refer to this strategy as the reverse chain rule. That technique is used to integrate a function with a different structure. It is discussed in a separate video. Last format. If we have a function which is a fraction with only one term in the denominator, we might have, for example, the integral of 3x to the 5th plus 4x cubed minus 2 in the numerator and 5x cubed, just the one term, in the denominator with respect to x, we start integrating by using the same approach as we did for differentiation. We divide all numerator terms one by one by the denominator term, and then integrate each term separately in the usual way. So splitting up our problem, we have 3x to the fifth over 5x cubed plus 4x cubed over 5x cubed minus 2 over 5x cubed dx. Then we can rewrite each of the terms, putting the numbers and the fractions at the front of the integral sign because they don't come into the actual calculation, and then bringing any terms in the denominator back into the numerator. So we have 3 over 5 x squared dx plus 4 over 5 integral of 1 dx minus 2/5 x to the minus 3. Now we do our normal thing there, rewrite the number 3/5, add 1 to the index, x cubed divided by 3 plus 4/5 times x minus 2 over 5, and then x to the minus 2 over minus 2. Tidy all that up, cancelling and changing signs, we get x cubed over 5 plus 4x over 5 plus 1 over 5x squared plus the location constant c. So you should now have the steps to be able to integrate a wide range of basic types of functions. Thanks for watching this video. In the next video in this series, we'll look at using the integration techniques to calculate areas under curves. Hit the like button and subscribe if you haven't already. Also go and do some questions in Test Yourself 1 on my website at drjamesmath.com. Add a comment below if you have any questions. Good luck. See you in the next calculus video.